Okay. Okay, recording in progress. Good. So again, hello everyone. I'm Maria Conti. I'm from University of Insubria. And today I wish to speak to you about the contents of this paper here, which is our latest published result, which you can find here. By our, I mean it was made in collaboration with Professor Alfio Bonanno from INAF, INFN Catania, and Professor Dario Zappalà from INFN Catania. And again, today the topic is going to be the conformal sector of quantum Einstein gravity beyond the local potential approximation. So to start, I want to illustrate you the abstract because it's going to serve to us as a menu of what we're going to see. So this seminar will revolve around the analysis of the conformal sector of quantum Einstein gravity. We'll talk a bit about that with an improvement due to the study of the role of the anomalous dimension, which we'll see it will actually get dynamically determined by employing the functional proper time flow equation. And in particular, and this we'll see with great care, the presence of the anomalous dimension will modify the background independence implementation scheme. And then from this implementation scheme, we'll see that not a single fixed point is going to appear for our model, but a full fixed point line, which is going to depend on this anomalous dimension, which you can think as a parameter in a sense. And of course, together with this fixed point line, we'll also talk about the critical manifold. So to start off, I wish to speak to you about the conformal sector in asymptotic safety and why we care about this. And to do so, I want to refer to these two very important papers by Voigt and Beyer, which you can find here, where they basically show the very central role of the conformal sector in the emergence of the UV non-Gaussian fixed point together with its critical properties. The idea is that while in classical GR, the conformal factor is not a propagating degree of freedom, in quantum gravity, actually its fluctuation dominates the path integral. And this is due to conformal factor instability, which is a fancy word for saying that the corresponding kinetic term has the wrong sign. So the overall effect of this is that the conformal factor fluctuations actually become dominant in the UV near the non-Gaussian fixed point. So in a sense, this is the big sum up of why we care about the conformal sector. And in particular, we're going to implement the background field method. So we'll see that the background field plays a very special role in the construction of the Wilsonian RG equation. So the idea is that we start with a fundamental action S of chi, where chi is a fundamental field, which we split into two components. Where one is chi b and the other one is F. While chi is playing the same role as the microscopic metric gamma mu of the full theory, chi b is playing the same role of the background G bar mu. So we know it is defined for practical computations, but overall has no physical relevance, and this is very important. And similarly, F is playing the role of the fluctuation field, which has to be quantized and goes by the name of H mu usually in the full theory. So the same ideas, it's just a conformal sector. The point is that at the end of our computation, we actually want for the fluctuation field to be dynamically determined by imposing this through this requirement, which is asking that the average of the fluctuation field must be 0. Why? Why do we care about this? Well, because if this is true, then any defined length is then proper with respect to the background, which is the only surviving metric in a sense. So in a sense, we won, okay, because we were able to define length and the cutoff, okay, which is now proper to the background, which once again, we defined exactly because we needed to do practical computations, but overall must have no physical relevance. So what happens? Well, you start with a conformally reduced theory, so you have this conformal field phi, which is defined as the average of that fundamental field chi, which is split into two components. Okay, and this field phi is the one appearing inside the Weyl transformation connecting this metric G mu to the reference metric G hat mu in a sense, okay? And together with this relation, we can write a very similar relation regarding just the background component. So G bar mu is connected to this G hat mu through this conformal factor chi b, which is just the one related to the background. But why do you care about this? Well, because from this relation here, we get another interesting relation regarding the momenta related to the two different metrics. Okay, so you can see this K bar here and K hat here. Okay, why do we care about this then? Well, because we are following background field method. Okay, so following Reuter's prescription, in order to maintain background independence, the traces inside the flow equation must be performed over the modes of the box operator related to the background. So this box here. Meaning, when we have to do an integration, we have to integrate over these guys here, which are specified by these equations. That's why it is so important. At least this is what happens usually, okay? But before moving on, I want you to be a little more convinced on the usefulness of the conformal sector, because I was very schematic in telling you how it works, but I want you to understand that it is a good thing to do, maybe. So to do this, I'm going to present you some results. Not surprisingly, I'm starting with some results by Reuter and Bayer, once again, where they studied the conformal sector of Einstein-Hilbert truncation through the vectoric equation, which we all know and love. Here it is in all its glory. So the idea is that they started studying this model here through this equation here, and what they get is a UV attractive non-Gaussian fixed point with, of course, its critical exponent, which share this form here. So they have a real part plus minus an imaginary part. So what this is telling you, it's that you have a trajectory which looks like a spiral going towards the non-Gaussian fixed point in the UV. Sorry. And why is this important? Because it is the same thing that happens in the full Einstein-Hilbert computation, where by full, I mean keeping track of all the degrees of freedom of the metric, not just the conformal sector. So this is very promising. Very briefly, other promising results in this sense are found inside this work here, back from 2012, from Professor Bonanno and Filippo Guarnieri, where they basically studied the same model, the same model through this other equation here. So not the vectoric equation, but the one loop RG flow equation. I'm going to talk more about this in a short while, because this is going to be the flow equation accompanying us until the end of the discussion. But basically, they do the same thing, and that, as you can see, this is exactly what happens. You have this spiral going towards the non-Gaussian fixed point in the UV. Great. And then there is also this more recent work, again, from Professor Bonanno, myself, and Sergio Cacciatori, who should be in the audience, where we studied the same model in a sense, but with an extra truncation. As you can see, there is a Ricci to the power 2 here. And we studied it through this same one loop RG flow equation. And this is what we get. We get, once again, a trajectory which is spiraling toward the non-Gaussian fixed point. And once again, this is important because it is the same behavior which is found keeping track of all the degrees of freedom, not just the conformal sector. So once again, this is promising. Let's keep looking into the conformal sector. Before moving on, here is finally that one loop RG flow equation. As you can see, it is definitely an RG flow equation. You have this RG time, which is usually defined as the logarithm of K, where K is the usual infrared cutoff. And what this equation is telling you is, what is it physically speaking? Well, it is a simplification of vectoric equation, because vectoric equation is, of course, exact, but it is very hard to solve. So this represents a simplification of it in the sense that it takes into account quantum correction up to one loop. Okay. The important part I want you to look at is this rho k here. This rho k is a regularizator, which is once again a fancy word for saying it is a function performing the cutoff. Okay. In particular, we usually use this regularizator family, which you can find here, where you can see that there are some things appearing. These gamma are just incomplete gamma functions, not important. There is an n appearing. This n is a parameter, a natural parameter, which is controlling the smoothness of the cutoff. So the idea is that the bigger n, the sharper the cutoff. And it is spectrally adjusted, and the UV cutoff lambda is sent to infinity, because we're just interested in the Wilson-Kadanoff portion of the RG, so no point in keeping things complicated, and we send this guy to infinity. And remember that this k hat has to be written in terms of this k bar through this relation we already talked about. This is what usually happens, okay? But we want to do something a little different. And this is by adding the anomalous dimension inside the mix and see what happens. So I'm sure that you know everything about the anomalous dimension, but let me waste 3 minutes of your lives and speak about the anomalous dimension for a couple of minutes so that we have the same background in a sense. So actually, the anomalous dimension stems far from statistical mechanics. So I want you to take a look at this very simple model. So as you can see, you have a free energy. It is a free energy because we're in the world of statistical mechanics, but it's just an action. And this field phi is a spontaneous magnetization. And of course, this spontaneous magnetization is coupled to a source, which is the magnetic field. So very simple model. If you take this model and study its spatial correlation functions, which are defined here, what happens is that you see two behaviors are found. The first one is when this r, which is a distance, the distance between this point x and y, is well below the correlation length psi characteristic of the model, then these spatial correlation functions decay as a power. While in the opposite case, they decay, but as an exponential. And we'll see that we're interested in the first behavior. This is the interesting one. Why is that? So I'm supposed to generalize that model. Okay, so you keep the same model actually, and you add as many terms and interactions and coupling as you'd like. Actually, there is a coupling which I'm not writing here, which is the one related to the kinetic term. Why do I not write it? But, well, because as Percacci and Perini actually showed in this very nice paper, this coupling is essential only when you're in gravity. So you're interested in what the beta function for this coupling looks like only when you study gravity. But inside this realm, it is inessential. So I'm not even bothering to write it. But apart from this problem, you start from this model, and what do you do? Well, you do your usual RG procedure. So you start with a theory, which is defined on a lattice with a certain UV cutoff lambda. But for some reason, you're just interested in physics, which is happening at very big scale, so above a certain length L. So in your next RG step, what you do is define a new cutoff, a more useful one if you want, which is lambda prime, and is defined as the old lambda over a certain number zeta, which has to obey overall that lambda prime is much bigger than 1 over L. So the idea is that you end up with a new theory, which is describing just the physics at very big scales you're interested at. Okay, this is the usual RG procedure. But what is the point? Well, the point is that the correlation length is psi and is, of course, a length. So after an RG step, it must scale as such in a similar way. So psi prime must be the old psi over that number zeta. So what is the point? The point is that when you get to the fixed point, either it is 0 or it is infinite. And in our case, we care about the latter case because it is the non-trivial one. So let's go back to here. Psi is infinite. This must happen. The only thing that can happen to our model is that the spatial correlation function must decay as powers, where we may have some freedom. For example, we could at least choose the exponent of such power. So this I do by parameterizing it, adding this eta. Well, actually, someone could step up and say, no, you cannot do that. You do not have that freedom because by very simple dimensional analysis, you know that the dimension of the field phi is d minus 2 over 2. And if you take this information and plug it into here, you get that eta is 0. Done. Well, no, because this is false experimentally. So what the heck is happening? The point is that maybe we have been a bit more, naive with the RG, because you could just say, well, an RG step is an easy thing to do. You just start from x coordinates and land to x prime coordinates, which are defined as x over that famous number zeta, okay? But the point is that, well, this is true. This is what happens to the coordinates when you perform an RG step. The point is it looks like that the field phi is getting dressed in a non-intuitive way when you do so, leading overall to a field which acts as it has a dimension which looks like this, so with an extra eta appearing on top of here, where eta is different from 0, and for a very obvious reasons we call anomalous dimension. So enough with the introduction. Allow me to stop for a second so I can drink a bit. Okay. And we finally get to main content of this presentation, of course, which is, again, the contents of that paper I mentioned at the very beginning. So where do we start from? We start, again, from the Einstein-Hilbert action. There it is, hopefully to get something different by adding that anomalous dimension. So what would one do usually? Well, you can start with this action, you perform your binary scaling, where this parameter nu here is usually chosen as 2 over d minus 2. This is very standard procedure. You do this, and you end up with your conformally reduced effective action, which looks like so. As you can see, there is this A appearing. It is just a constant depending on the dimension. And you also have your normalization function zk, which is basically defined as -1 over the Newton's constant, running, clearly. And you also have your running cosmological constant. Well, actually, we want to be a little more general. Okay, so instead of studying that action, we study this action, this effective action here. So as you can see, we have a kinetic term and a perfectly general potential term. We do this, once again, because it allows us to be a little more general. But by choosing a proper truncation for this potential, we can easily go back to this picture here, okay? So what would be the standard procedure in this sense? Well, you take this effective action, you plug it into your, one loop RG flow equation, where you study this family of cutoffs, where you have to remember that the trace must be performed over the modes of the background, where you remember that these box operators are related to one another through this relation, which leads you to this relation regarding the momenta. Great. And from that point there on, you have to plug this relation everywhere. Every time there is a k hat appearing here and there, you have to plug this into it. So for example, the scaling of this family of cutoffs looks like this. Okay, as you can see, there's this chi b appearing pretty much everywhere. This is what happens usually. But for us, we do something different. We finally insert this anomalous dimension. And this we do by considering an anomalous dimension, an anomalous scaling for the background. So in general, usually this field here, the chi b, should be dimensionless. But we do something different and suppose it actually scales due to the anomalous dimension. So we define it as such. What is the difference? Well, the point is that this relation regarding the two box operators is the same. This does not change. This is the same. What we are changing are the dimensionalities of things, of course. So the idea is that if we wish for our first operator, box operator, to hold its usual dimensionality, so it's just a momentum square, the other one must scale as such, okay? Because there's this chi b, which is not dimensionless now, but it involves eta. So what is the point? If before this relation led us to this relation here for the momenta, now this very same relation leads us to this one. Okay, so for example, the old scaling for the cutoff now looks very similar, but there is this minus eta nu appearing everywhere, which is a small difference, but it is going to entail big differences. So in that way, we got what happens if you insert the anomalous dimension. We're actually quite ready to start solving the one loop RG equation. Okay, left-hand side, that's not difficult to do. You just perform your RG time derivative on your effective action. That's it. That's the easy part. The hard part is try to understand what the right-hand side of the flow equation does. And this we do by expanding it as such. When from this point until the end of the world, we have to say that the trace must be performed over these modes. So as you can see, here I'm adding this G bar, and we are integrating over P bar, etc. Great. Notice that at some point we would like to, recover the differential equations for this guy here and this guy here. Can you see my cursor, by the way, if I highlight stuff?
Yes, it's small, but we can see it.
Okay, great. So if we want to compare the two, at some point we have to insert the relation linking G hat to G bar, okay, if we want to compare the two. But the point here is that we have to write G bar and P bar and so on. This we do, this guy, we know this is the scaling of the cutoff. We already told how it looks like. This is the next step to do. This we have to calculate. And this we do by performing our Baker-Campbell-Hausdorff expansion, okay, because this guy here is composed of two terms. So in general, we have to perform this expansion, where in general, these B1, B2, B3, and B4 coefficients look like this. So for our model, what happens is the following. As you can see, this is the right-hand side of the flow equation. So for example, here we have, again, we inserted that relation regarding G bar and G hat so that we could compare left-hand side and right-hand side. Again, we know what this looks like. Here we expanded stuff. As you can see, there's this minus eta nu appearing. And here we did our Baker-Campbell-Hausdorff expansion, which in general looks like this. And for us, it looks like this. Okay, so these are the computations. This we do, then we have to integrate over P bar, then we have to compare to what happens on the left-hand side, and finally, we get the differential equations for Z and V, which I remind you that they are the renormalization function and the potential, which look like so. Actually, I'm hiding a part of the story in the sense that, as you can see, that there are some objects appearing here which I'm not stating what they are inside this presentation. These are very convoluted functions of other things appearing inside this slide, and there are coefficients F0 and R0 and T0 which I'm not stating. But the point is, if there is one thing I want to mention is that, as you can see, there are some derivatives appearing here and there, and these are taken with respect to the field phi. But overall, these are not the differential equations we are interested in, because we're interested in the differential equation for the dimensionless counterparts of these objects. So these I finally introduce. I call big Yk as the dimensionless counterpart of the potential, and I call small zk the dimensionless counterpart of the renormalization function. So what is the point? Well, the point is that, yeah, we had to insert this anomalous scaling for the background. So we have to do the same for the whole field, okay? So in general, they share the same structure, of course, but in general, this dimensionless counterpart for the whole field, which we call big X, is different from this psi b. Here comes the simplification. Now that we did all of our computations, because we already got our differential equation, we performed the so-called single field approximation. And by this, I mean that now, only now, the expectation value of the dimensionless field X, which is this guy here, is identified with the background psi b, which we now indicate with small x from now on because it looks better. So what is it that we're doing? The point is that we're not bimetric, okay? Because yes, we're using the background field method because, of course, at some point you have to introduce a background in order to perform computations. And this we do by trying to solve the one loop RG flow equation with the expectorally adjusted cutoff that I showed you before. We do all of our computation, and just at the end, we perform the single metric approach. So only at the end, we identify pi b with the average value of the whole field phi. So where is the trick? The point is that through single metric approach, at the end, we identify the background and the total field expectation value. But at the beginning, these two guys were very well separated, okay? So this box operator and this other box operator were very different, okay? And this difference is the one that made us able to introduce eta, okay? Then we do all of our computations, and at the end of them, we perform this single metric approach. But eta survives this identification, and we end up with differential equations for the dimensionless counterparts, which look like so. Once again, I'm hiding something because I'm not stating what these guys looks like. If you actually expand these two differential equations, they look horrific. So in order to understand what they're telling you, you have to resort to something. And this resorting to something for us is to consider the limit of n to infinity, where n, in case you forgot, was that number telling you how sharp the cutoff was. So physically speaking, we're asking ourselves, what happens if the cutoff is really, really sharp? And this is what you get. These are the final differential equations we're going to work with, which will accompany us until the end of this presentation. And as you can see, they look far more manageable. So again, sorry, a little pause for me to drink. Okay. So, of course, the next question is, Great, you got your differential equations. What do the fixed point look like? How is it the fixed point structure for these differential equations? Well, actually, I have to answer another question before this one, which is what happens if you choose this exact truncation for z and y inside those differential equations? Well, if you do this, you see that what happens is that you get no dependence on the field x for the previous differential equation. So you end up with two fixed point, purely algebraic equations, which look like so. Of course, you can ask me, yeah, why this set of monomials? What does this represent? Let me go back a bit. Sorry, bear with me. Okay. Remember where I started and said, yeah, but for us, it makes sense to be a little more general. We're going to study this effective theory, which is actually composed of a kinetic term and a perfectly general potential term. But it is very easy for us to go back to this very specific description by choosing a proper truncation for the potential. Well, that is the truncation. Okay, that is exactly the truncation, which allows you to go back to Einstein-Hilbert for d equal 4 in particular. So that's the physical meaning of that truncation. What is even more interesting is that, well, what happens is if instead of using these monomials, you use other polynomials. For example, you study this guy and then you sum other powers together with their own coefficients and you plug them into the differential equation you're studying. Well, what happens is that all the coefficients go to 0, all of them, except these monomials, which now look like that they are the only FP solution. Okay, so these are the only ones you can study. You plug them into your differential equation and you get these algebraic equations, which look like so. And what happens? Well, you see that you have two equations with three parameters. You have this u, this w, and of course your eta. So this is not a single fixed point. This is a fixed point line. Which we parameterize by eta in particular. So as you can see here, you have a plane, which is spanned by u and w, and eta is scanning through the fixed point if you want. So as you can see, there are three branches, basically, depending on the range of eta you're studying. The blue range corresponds to eta lower than 1, the red range corresponds to eta bigger than 2, and then you have the middle range, the green one, between 1 and 2, okay? And inside this picture, U is playing the same role as the dimensionless cosmological constant lambda from the Einstein-Hilbert truncation, of course, and similarly, W is playing the same role as the dimensionless Newton's constant G. Okay. Well, this is interesting. What is even more interesting is trying to understand what happens to the critical manifold. Okay, and this we do by studying perturbation around the fixed point. So we use these. Okay, as you can see, we create these perturbations, which we call H and F, related to this dimensionless potential and dimensionless renormalization function, respectively. And these are the fixed point coordinates, if you want. So you take these guys, you plug them into those differential equations, and what happens? Well, this is what happens. Once again, you see that for a very specific monomial form, both for F and H, the linearized flow equations, once again, they become field independent. So this is what you do. You choose F and H to be monomials. As you can see, P and Q, they're just non-negative integers, while S and R, they're just constants. You plug them into those differential equations and you see that the problem is once again reduced to a set of algebraic equations, which look like so. In particular, you see that on the right-hand side that this theta, in case you missed it, was this guy here. They're just the critical exponents, okay? So the sign of theta is going to tell you if the direction is attractive for positive theta, and the opposite case, you have a repulsive direction. So these are the equation, and it is very, very easy to see that when Q is equal exactly to P plus 4, then they get these equations, they become independent on X. Very easy to see. So the idea is that we finally found our eigenfunction spectrum. It is discrete, and it looks like so. So the first eigenfunction looks like this. The second one looks like this. You have to scan following this rule, etc., etc., etc. So it is a discrete spectrum, and it has infinite components, if you want. This is the eigenfunction spectrum, but what do the critical exponent behave like? The answer is, well, that still depends on the range of eta that you're studying. So, for example, in this plot, I'm plotting what happens when you look in the blue range, so when eta is below 1, or in the red range, so when eta is bigger than 2. And the idea is that in these ranges, the eigenvalues show once again this form that we already encountered. So they have a real part plus minus an imaginary part. In particular, these eigenvalues are actually related to one another. So I'm bothering to plot just one of them. Okay, one for each value of eta scanning through these bars here. I'm going to comment the actual contents of this plot in a short while, but before doing so, let's perform a check, because yes, we were able to understand what happens if you add the anomalous dimension, but do we recover the same things without the anomalous dimension? Do we get the same results as this paper here when we implement eta equals to 0? Because if we do, then we should get back that old Reuter fixed point, which showed in particular positive coordinates for the fixed point. Does this happen to us? Let me go back for a second. This is the fixed point line plot. Eta equals 0 is somewhere inside the blue range. This is the first quadrant. Yes. Okay, so this is good. We get the same thing. This is the first check. Second check, what happens to the critical exponents? Well, in the old work, let me call it old work, the old Reuter fixed point showed these critical exponents when you studied the, again, sharp cutoff limit. What happens to us? We have this plot. Let's try to understand. Well, first question, which is the eigenfunction we should study? Well, clearly the first one, because it is the only one showing a positive real theta, so it should be this one. What happens at eta equals 0 inside this? The very same critical exponents. Okay, check is done. We shouldn't have done anything too stupid, at least. But let's move on. What happens when you're inside the green range instead? So when you're lying in between 1 and 2? Well, a bit more weird thing happens. You get two eigenvalues different from each other, which are purely real. So actually here I'm reporting both of them because they're different. And we have both θ1 and θ2 on these axes. So let's try to see what they mean, these plots, because I was very schematic in telling you that, yes, these are complex eigenvalues, these are real eigenvalues, but it didn't explain pretty much anything. So let me drink again for once. Okay. What happens inside the blue range? First question. So eta below the value of 1. Once again, complex values, okay? So as you can see on the x-axis, I plot real theta, and on the y-axis, imaginary part of theta. In particular, I know that this image is very, very crowded, but just look at the blue parts, okay? In particular, I want you to focus on the first eigenfunction, once again, the one I circled. The point is, this is probably a bit faint, but as you can see, there is a point from which the blue line always lies inside the first quadrant. Okay, as you can see, there is a point from which, there it is, first quadrant. The idea is that then, when this eta is below this critical value, eta critical, which is around 0.96 more or less, this line is inside the first quadrant. So that means that we found a relevant operator, because real theta is always, the real part of theta is always bigger than 0. So it corresponds to a relevant operator. It is an attractive direction. But what about all the other operators? Well, as you can easily see, they always lie in this quadrant. Here I'm plotting just the first two of them, but if you plot all the infinite eigenfunctions, they all lie inside here. So this corresponds to all irrelevant operators. What is the meaning of this? Well, the idea is that we ended up with a discrete eigenfunction spectrum, which was a bit alarming because, yes, it was discrete, but it was infinite. How do we get a predictive theory? Well, the point is that for a theory to be predictive, we have to count the relevant operators, okay, inside the eigenfunction spectrum, and we get only one. So if eta is below this critical value, then the theory is actually predictive. This is what happens to the blue range. What happens to the red range instead? Same picture, please shift your focus to the red lines. Opposite thing. Okay, as you can see, it is basically the flip of what happens to the blue range. So not much to say. You cannot escape the fact that this corresponds to a non-predictive theory because you have infinite relevant operators. So we have to ditch eta bigger than 2 range. That's the meaning of the red one. Finally, what happens in the green range, so between the values of 1 and 2? Well, once again, that's where we found that we had 2 real values, okay? I hope this picture is slightly visible at least. I know it's a bit crowded. The point is that for most values of eta, there are actually infinite relevant reactions. Let's look at it. Okay, first off, we concentrate on the first eigenfunction as usual. As you can see, it lies in the first quadrant. So both θ1 and θ2 are positive. So means that we have 2 relevant directions. Okay, what about all the other eigenfunctions? Well, I ask you to focus just on the green part. Okay, so forget for a bit about this yellow part. As you can see, if you follow these curves, you can see that you have both a relevant and an irrelevant direction because theta is bigger than 0, okay, relevant direction, but θ2 is lower than 0, irrelevant direction. So overall, we have infinite relevant directions. The end, for this range of the green part, if you want, no predictive theory can be found. But there's this very small range, the one corresponding to the yellow part of the bar, if you want, very small between the values of 1.8 and 2, where, as you can see, the first eigenfunction is once again relevant. But all the other ones are not. Both θ1 and θ2 are negative. So that means that once again, we have a predictive theory, even though it is a very small range. Moral of the story, what happens if we insert the anomalous dimension? Well, first off, we do not have a single fixed point. We have a whole fixed point line. Second part of the story, we get an eigenfunction spectrum, which is infinite but discrete, and yet we find some predictive portions of the theory, if you want. So there are some ranges of eta which correspond to a predictive theory. The first one, the main one, if you want, is a subset of the blue range. So if eta is lower than this critical value, then you have, once again, a predictive theory. There is also this small range inside the green range between the value of 1.8 and 2, which also corresponds to a predictive theory. Actually, some further studies should be needed for this latter range because this does not correspond with the usual spiral behavior we're used to because we have 2 real eigenvalues instead of two complex values. But apart from this problem, this is pretty much the content of my discussion today. Thank you very much for your attention. And of course, please ask questions if you have any. Thank you.
Let's thank Maria for the nice talk.
Thank you.
Let me stop.